Today we are going to discuss self-induction, and then we'll discuss what is self-inductance. What is the difference between self-induction and self-inductance? We'll derive expression for self-inductance of a planar coil and also of a long solenoid. After that, we'll discuss mutual induction. Again, what is mutual induction and what is mutual inductance that we'll discuss. We'll also discuss mutual inductance of two planar coil and two long solenoids. We'll also discuss energy stored in an inductor. What are Eddy currents? How they are developed and how we can minimize Eddy currents there. What are the uses of Eddy currents? So we'll discuss all these in today's discussion. Self-induction is the phenomena in which an EMF is developed whenever current linked with the coil or circuit changes with time. So it is the EMF developed in a coil or circuit whenever there is a change of the current there linked with that. Obviously, when the current is changing, magnetic flux linked with that will change. And if the magnetic flux is changing, in that case, there will be current developed or current will be induced. So suppose we assume that phi is the magnetic flux linked with a coil or a closed circuit. When there is a current I flowing through it, so obviously magnetic flux will be directly proportional to the current. If you remove this proportionality sign, in that case, we'll have to introduce some constant of proportionality. So that we represent it as L, and it is your L into I now. This L is called coefficient of self-induction, or it is called as self-inductance. This is called as the self-inductance. So we have the expression phi is equals to Li. Phi is the magnetic flux, I is the current flowing through it. And in that case, this L will be the coefficient of self-induction, or it is simply called as the self-inductance. If you take self-inductance, we can say that it is the property of a body due to which it will resist any change in the current linked with it, or any change of magnetic flux linked with it. But when you have to define that so that we can measure self-inductance linked with a coil or a closed circuit there, then we define it in the mathematical terms. Like, if you consider that phi is equals to Li, if I is suppose 1 unit, in that case, phi will be equals to L. So the coefficient of self-induction or self-inductance we can define as it is the magnetic flux linked with a closed circuit or loop when there is unit current flowing through it. So it is numerically equals to magnetic flux linked with that closed circuit or loop when there is unit current flowing through it. This is one way in which we can define self-inductance. Also, as we have the expression phi is equals to Li, phi is Li, suppose we differentiate it with respect to t, that is the time. So what we'll get? We'll get d phi by dt equals to L di by dt. Now, as we know that E is minus d phi by dt, so in that case, from this one, we can write that magnitude of E will be equals to L di by dt. Again, here, if I consider that di by dt is 1 unit, in that case, magnitude of E will be equals to L. So from this mathematical relation also, we can define self-inductance. We can say that the self-inductance of a closed circuit or coil or a loop is numerically equals to magnitude of the EMF induced when there is unit rate of change of current linked with this loop. This is the magnitude of the EMF induced or developed when there is unit rate of change of current linked with this. So this is how you can define self-inductance. If you consider the unit of self-inductance, this is Henry, which will represent it as capital H. So Henry is the unit of self-inductance. Suppose we want to find self-inductance of a planar coil. So suppose this is a planar coil of number of turns capital N, its radius is R, and through it suppose I current is flowing, which is changing. So at any moment, if you consider the magnetic field at the center of this coil, so magnetic field at the center of the coil, this is equals to mu naught Ni by 2R. This is the magnetic field at the center. So magnetic flux linked with each turn of this coil, magnetic flux linked with each turn of the coil, that will be equals to this mu naught Ni by 2R multiplied by pi r square, because this will give the area there. Now since it has capital N number of turns, obviously through the entire coil, if you consider magnetic flux, it will be N times of this one. Therefore total magnetic flux through entire coil, this will be equals to mu naught Ni by 2R into pi r square into N, or that we can write it as mu naught N square pi r by 2 into I. This is the magnetic flux. Suppose I call this as equation number 1. Now as phi we have represented as Li, where L is the self-inductance. So if you now compare equation 1 and 2, so from equation 1 and 2, what we get? L is equals to mu naught N square pi r by 2. This will give the expression for the self-inductance of a planar coil of capital N number of turns having radius r. Remember, we have considered there is air inside this. So in this case, we are taking mu naught there, air or vacuum, whichever is there. If suppose any other medium is there, which is changing the permeability there, in that case it is your mu. So in that case it will be your mu there, or you can write mu naught into mu r. Otherwise, in general, it will be this particular expression, unless it is mentioned that what is the medium there in the coil there or inside the coil. This is the expression for self-inductance of a planar coil. Now suppose you want to find self-inductance of a long solenoid. So suppose I have a long solenoid having a small n as number of turns per unit length, and I current is flowing through this solenoid. We assume that its radius is suppose r. So now as I current is flowing through this solenoid having a small n as number of turns per unit length, so magnetic field inside the solenoid, this is given as your mu naught Ni. This will give you the magnetic field inside this particular solenoid there. So P value is this much. If you now want to find magnetic flux through each turn of the solenoid, then this magnetic field value must be multiplied by the area of this that is the area of each turn of the coil there or the solenoid there. So this value of the magnetic field must be multiplied by area of each turn of the solenoid there. So in that case, magnetic flux through each turn of solenoid, this is equals to mu naught Ni multiplied by pi r square. So now, if you want to find total magnetic flux through L length, suppose I take that the solenoid part, it is of length L. So number of turns of solenoid over a length L. This is N into L, because N is the number of turns per unit length. We have multiplied it by the length of that particular part of the solenoid. So in that case, now the total magnetic flux, therefore total magnetic flux through L length of solenoid, this is equals to mu naught Ni into pi r square multiplied by N into L. This is the total flux. So this is written as phi equals to mu naught N square pi r square L into I. This is the equation 1. Now, as phi is equals to Li, this is suppose your second equation. So from equation 1 and 2, what we can get? We can get L equals to mu naught N square pi r square L. Because in this case, simply I term will get cancelled from both terms there. So in that case, it will be your mu naught N square pi r square into L. This is the expression for self-inductance of a long solenoid of length L or over the length L there. So this is the self-inductance of a long solenoid over length L. Now we want to find expression for energy stored in an inductor, that the magnetic energy is stored in an inductor. So suppose we have an inductor of inductance L through which I current is flowing at any moment. In that case, potential difference which will be developed across it. So potential difference developed, that will be equals to L di by dt. Basically, this is just the EMF which is developed there due to the self-induction which is getting produced there. So in that case, this is your L di by dt. So this is the potential difference there across this particular inductor. Now let delta Q charge be transferred in time dt. Suppose in time dt, we assume that delta Q amount of charge is flowing. So this dq, this is equals to your I dt, because I is your dq by dt, so dq will be your I dt. So now you can see that if dq amount of charge is flowing through this inductor, which is there under potential difference L di by dt, so a small work done. Therefore, a small work done in transfer of charge dq. This will be how much? It is your V into dq, because we can assume that this is suppose V. So it is V dq, which is your L di by dt into I dt. That can be written as your L I di dt, we can assume it is cancelled. Therefore, total work done when the current is changing from 0 to I. So total work done when current changes from 0 to I, or 0 to, suppose I represent it as capital I. So in this case, it is your W will be integral of this dW. This is your Li di, integral 0 to capital I. So this is your Li square by 2. And now we have to put the limit 0 to capital I, which is half L I square minus 0. That is your half L I square. So this is the expression for work done. Now you know that work done on a system is stored as its potential energy. So as the work done is stored as its energy, therefore energy stored will be equals to work done on the system. So this is your half L I square. So energy is stored there in the inductor will have the expression half L I square. L is the inductance and I is the current there. Let's now take mutual induction. Mutual induction is the phenomena in which an EMF is developed in a coil whenever current in a neighboring coil is changing. And the current in the neighboring coil is changing in such a way that it is changing the magnetic flux linked with the second coil. So here, this is basically a phenomena associated with two coils there. So it may be two coils or it may be two solenoids there, but basically there will be two things there, either coil or solenoid or any such arrangement which we are taking. We are changing current in one coil and there is another one which is kept close to it, so that due to the change of the current in the first coil as the magnetic flux is changing, this is also going to change the magnetic flux linked with the second one. And if the magnetic flux linked with the second one is changing, there will be definitely current induced in the second coil. Like you can take it in this way. Suppose I have a coil. This is the coil. Here it is connected to a switch there. And if you pass current and the current is suppose changing there, basically when we switch on or switch off, then only the current will change. After that it will acquire a constant value there. And you have another coil there which is kept close to it. So if you consider that there is a current flowing through it, so obviously there will be magnetic flux linked with this one, and this is also going to flow through this one. So what will happen? You will find that the magnetic flux, if it is linked with the first one, it is also going to change the magnetic flux to the second one. So here, this is not connected to any source. This is connected to a source, say battery is there. But this is not connected to any source. What we find when we switch on it or switch it off, so that the current linked with this one is changing, there is a deflection shown in this ammeter there. If there is an ammeter or galvanometer which you have connected, it will show deflection. That deflection will indicate that there is definitely some current developed. There is no other source connected there, conventional source we have not connected like a cell or battery. Still there is deflection shown here. So this is basically due to mutual induction. Normally, the coil or the circuit in which we are changing current, we call it as the primary circuit. So suppose this is the primary, and the second one in which we are observing its effect, or the coil in which, or the circuit in which current is induced as a result of change of the current in the first one, that is called as the secondary coil. So again here, suppose I take them as a coil number 1 and coil number 2. So if suppose you have magnetic flux linked with the second one, or say secondary one, this is proportional to the current flowing through the first one. Magnetic flux linked with the second one will be proportional to the current which is flowing through the first coil or the circuit there. Or we can write phi 2 equals to some constant of proportionality, that we write it as your M. And this M is called coefficient of mutual induction or mutual inductance. So this is one expression. Suppose I differentiate it, then we have d phi 2 dt. This is equals to M di1 dt. Now as E2 will be equals to d phi 2 dt, EMF induced in the second one will be proportional to the rate of change of the flux linked with this. So this E2 will be equals to minus d phi by dt, d phi 2 dt. Or what we can get it from this, that magnitude of E2 will be equals to M di1 by dt. So here from these two expressions, whether this is the first one or the second one which we are using, we can define mutual inductance. So here, if suppose I1 is 1 unit, then what we get? Phi 2 is equals to M. So we can define that mutual inductance of two coils will be equal to or numerically equal to magnetic flux linked with second coil when there is unit current flowing through first coil. Or you can simply say it is the numerically equals to magnetic flux linked with one coil when there is unit current flowing through the other coil. Or if suppose di1 by dt, this is your 1 unit, then E2 is equals to M again. So from this we can define that mutual inductance is numerically equals to magnitude of EMF induced in one coil when there is unit rate of change of current in the other coil. So this is how we can define mutual inductance. Now again, if you consider the unit of mutual inductance, in that case it is same as that of the self-inductance. So the unit of mutual inductance is Henry. So whether it is your self-inductance or mutual inductance, both have the same unit, Henry. Suppose we want to find mutual inductance of two concentric coplanar coils. We have here two coils. N1 is the number of turns in the first coil. N2 is the number of turns of the second coil. First coil has the radius R1 and second one has radius R2. We are passing current I through the first coil. Magnetic field intensity at the center of second coil this is equals to mu naught N1 I by 2 R1. Why is it so? Basically, we take the magnetic field at the center of the first coil. That will be equals to mu naught N1 I by 2 R1. And now, since the two have been kept coaxially and they are concentric, in that case, the magnetic field at the center of the second coil will also have the same value. So now, if you consider magnetic flux through each turn of second coil, that will be equals to mu naught N1 I divided by 2 R1 into pi R2, because R2 we have taken as its radius. So in this case, this is the magnetic flux through each turn of the second coil. Therefore, total magnetic flux through second coil, that will be equals to mu naught N1 I into pi R2 square by 2 R1 into N2. So this is your magnetic flux through the second coil. Now, this suppose I am calling it as equation 1. Now, as phi 2 is equals to m I, or basically m I1 it is there, but we have assumed the current as I, so it is written as I. So this is your second one. So now from first and second, from equation 1 and 2, what we get? M is equals to mu naught N1 N2 pi R2 square by 2 R1. This is the expression for mutual inductance of two planar coils which are concentric and coplanar. Now suppose we want to find mutual inductance of two long solenoids where one is wrapped over the other. So this is suppose one solenoid. Suppose it has a N2 number of turns per unit length, its radius is R2, and over that we have another solenoid having N1 number of turns per unit length and radius R1, which is wrapped. Suppose I is the current flowing through the first solenoid. So in this case, magnetic field intensity due to first solenoid, this is equals to how much? It is your mu naught N1 I. And since the two have been kept along the same axis, so this is also the magnetic field inside the second solenoid. So magnetic field, and this is equals to magnetic field intensity inside second solenoid. Why? Because the two have been kept along the same axis. One is wrapped over the other. So now we can find what is the magnetic flux through each turn of the second solenoid. So magnetic flux through each turn of second solenoid, this will be how much? This is your mu naught N1 I multiplied by pi R2 square. Because R2 is its radius, so its area will be pi R2 square. Now if you want to find total magnetic flux through the entire second solenoid or over L length of the second solenoid, so magnetic flux through L length of second solenoid, that will be equals to mu naught N1I pi R2 square multiplied by N2 into L, because this N2 into L will give you the number of turns of second solenoid over the length L. So this is the total magnetic flux through the second solenoid. So this is equals to mu naught N1 N2 pi R2 square L into I. This is your phi 2. Suppose I call it as equation 1. Also, phi 2 by definition we have taken as Mi. This is the second one. So from equation 1 and 2, what we get? M is equals to mu naught N1 N2 pi R2 square L. This is the expression for mutual inductance of two long solenoids over length L. Here we have assumed that the current is flowing through the first solenoid, and this is the mutual inductance. What will happen if the current flows through the inner one? If you consider the current flowing through the inner solenoid, in that case, what is the expression for the mutual inductance there? So let's see whether we get the same expression or some different expression there. This time we are assuming that the current is flowing not through the outer one, but through the inner solenoid. So I is the current flowing through the second one, whose radius is R2, and R1 is the radius of the outer solenoid. So now this time magnetic field will be due to the second solenoid. And how much it will be? Now it will be equals to mu naught N2 into I, because this time current is flowing through the inner one. So this is the expression for mu naught N2 into I. So obviously this is also the magnetic field inside the first solenoid, because both are kept along the same axis there. Now if you consider magnetic flux through each turn of first solenoid, how much it will be? It will be equals to N2I into pi R2 square plus. Now how we are taking this one? Suppose this is the cross-sectional view of the inner solenoid. This is of length, radius R2. This is the one which is that of the outer one. This has radius R1. If you want to find magnetic flux through each turn of the first solenoid, then we can consider what is the magnetic flux through this inner one and what is the magnetic flux through this part. That is portion outside the first solenoid, that means inner one. So we can find total magnetic flux. What is the magnetic flux through the inner solenoid and what is the magnetic flux through the region which is between first and the second solenoid. Magnetic flux through this part is your mu naught N2I into pi R2 square, because this radius is R2, plus magnetic field value, suppose I call it as B dash, into pi. How much is this particular area? This is your pi R1 square minus pi R2 square. This is the expression. Now you see, my current was flowing through the first inner solenoid, and that value is your mu naught. Magnetic field is mu naught Ni. If the current is flowing through a solenoid, the magnetic field inside the solenoid is given as your mu naught Ni. whereas outside the solenoid, magnetic field is 0. So if the current is flowing through this part or this inner solenoid, this value of magnetic field, which is the magnetic field in this region, that is between first solenoid and the second solenoid, the gap between the two, or you can say outside the second solenoid, this term will be 0. So if this term is 0, that means this part will have no contribution. So magnetic flux through each turn of the first solenoid will just be equal to magnetic flux which is flowing through this inner solenoid. So this is your mu naught N2I into pi R2 square. Now if you consider magnetic flux over L length of first solenoid, so in that case this will be equals to this, it is your N2, this is your N1 now. So in this case what you will get? Mu naught N2I as it is pi R2 square, and over a length L of the first solenoid, it is your N1 into L length, N1 into L will be the number of turns. So in that case, this is equals to mu naught N1 N2 pi R2 square into L into I. This is 5. Now you can see that from equation 1 and 2, if you just compare, the value of the mutual inductance will be mu naught N1 N2 pi R2 square L. This is the same expression for mutual inductance of the two long solenoid over a length L. That means what we have shown, whether the current is flowing through the outer solenoid or it is flowing through the inner solenoid, mutual inductance of the two will remain the same. Let's start. What is eddy current? Eddy currents are the current which is developed on the surface of conductor, which is subjected to a change of the magnetic flux. Suppose you have a thick conductor and it is kept in a region where magnetic flux is changing. In that case, whatever current is developed there in that conductor, we call it as the eddy currents. Now, why we are getting that eddy current? Suppose you have a particular conductor, it is a thick conductor, suppose it is subjected to a magnetic field, and that magnetic field is suppose changing there. So obviously all the free electrons of this particular conductor, they will experience force, and due to that they will be moving. Now if they are moving there, since we have not subjected to any full path there, like you have not made it a closed circuit there, so they will just try to move so that they will just move as they are under the influence of a force which is they are experiencing. So what they will do, they will form a loop which will be circular. So in that case they will try to move inside it, and there, as these electrons, which are the free electrons, as they are in motion, as they will be repelling one another also, so they will try to move to the maximum possible loop length there, and they will form eddy currents there in the conductor. So basically when you take this EMF which is developed in the conductor, it is given by rate of change of the flux. So this E, which is the EMF developed, and this is your rate of change of the flux to which it is subjected. So the eddy current which is developed, we can write it as E by R. This R will be the resistance of the conductor. Now since the conductor has very small resistance there, in that case what will happen? As this R value is very small, in that case the current value will be very large. So there will be large current developed in the conductor. And this current, which is large in magnitude, this can produce a heating effect there in the conductor there, and there will be energy loss due to that. So in that case, what we do, we try to minimize eddy current. And for that, we are using laminated sheets of conductor instead of using thick conductor there. Of course, there are some uses also of eddy current. That means there are some areas in which we can use eddy current as an advantage. So there, definitely that part will be there, but still there will be energy loss in the form of heat due to the eddy current in the conductor. And here, to minimize those eddy currents, if you consider that instead of using thick conductor, if we are using laminated sheets of conductor. Now to understand that, just take it in this way. Suppose you have a square plate. In this, suppose the length is 20 centimeters. Here, if the current is developed and is forming the loop there, then we can assume the largest loop which will be there, that one will have the length which will be proportional to 80 centimeter. That will be the perimeter here. So in that case, as they will move to a larger length, definitely they will be doing more work there. So the value of the eddy current will get reduced. So what we can do, suppose if we consider that we have cut that one into two parts. So now if it is cut into two parts, then what will happen? You will have the loop there developed in these two parts, suppose. Now here, if you consider the length of loop in each part, in that case, how much it will be? This is 20, 20, and this is 10 and 10. So it is 60 for one and another 60 for this one. So it is total, it is your 120 centimeter. That means now the length of the loop has increased, so they will be doing more work there. So the eddy current value will get reduced. Suppose I cut it again into two more parts, so that now this type of loop will be there. Now for each one, here it is 20, this is also 20, this is now 5 and 5. So that means the length of the loop, largest loop in one part will be of 50 centimeter. And since there are 4, so in that case it will be your 200 centimeter. So what will happen? Here, as you are cutting it into different parts there, length of the loop is increasing, so effective value of the eddy current will get reduced. So that is why we use laminated sheets. Now why we are using laminated one? So first of all, instead of thick, we are using the sheets of that. Instead of using thick conductor, we are using the sheets of that conductor. And they all are laminated, so that they are not in electrical contact with one another. Otherwise, it will be as good as a thick conductor. So here, this is the reason. Of course, you can explain this, like if suppose the conductor has, say like this one. This way also you can consider that as these are the having cuts, in that case, we have increased the length of the loop there, and in that case, the eddy current will be reduced. So this is how we can reduce eddy current. And this we are doing by using laminated sheets of the conductor instead of using thick conductor there. Applications of eddy current. The main applications of eddy currents are there in deadbeat galvanometer, induction furnace, speedometer, and magnetic brakes. So in deadbeat galvanometer, what actually happens, like if suppose you have a galvanometer, you have passed electric current through the galvanometer for measuring it. So there, if you have taken one particular observation, in that case, what will happen? For taking second observation, you need to wait till the coil comes to rest. Or you take it in this way, you have passed electric current. When the current will pass through the coil of the galvanometer, in that case, it will turn. It will acquire an equilibrium at one particular position. we measure at what angle it is oriented there. And now you want to take the second observation. In that case, what will happen? You will switch off the circuit, and as soon as you switch it off, in that case, it will be no current flowing through the coil, so it will try to come back to the original state. And there, if you want to take the next reading, then next reading you will take, or you will switch on the circuit when this coil comes to equilibrium or rest condition. But here what happens, once you have switched off the circuit, coil is coming from the equilibrium which it has acquired when the current has passed, and now it is coming back to the case when there is no force experienced by that coil. So it will turn. But in that case, due to inertia, it will be making oscillation there, and it will take time to come to rest. But what actually happens there in the galvanometer, if you have now here the coil is moving there in the region of the magnetic field produced, there are the field pole pieces of the magnets which is producing magnetic field. So in that case, if inside the coil we have the laminated core there, in that case what will happen, the moment the coil turns, magnetic field or flux linked with that core will change. So there will be eddy current developed there, and the direction of the eddy current will be such to oppose the cause which is producing it. And what is the cause of that magnetic flux change? It is the motion of the coil. So in that case, it will try to oppose the motion of the coil and will try to bring it to rest as soon as possible. So a large opposition will be produced there to the motion of the coil, and it will come to rest position very soon. And this happens so fast there, that means just by making one or two movement, it will just come to rest. So that is why it is also called as the deadbeat galvanometer. It is called as the deadbeat galvanometer. Damping is very high there. Another is the induction furnace. In induction furnace, we have a high frequency oscillator there, and which will be producing magnetic flux in a particular region. And since it is a alternating one, it will be changing the direction. So now if I put any conductor there in the field, in the region where the field is being produced, in that case there will be flux change linked with that conductor. So there will be eddy current developed, and as the eddy current is developed, there will be heat produced in it. And since it is a conductor, its resistance is very less, so the eddy current will have a very high value. As a result, what will happen, that particular conductor will have so much large amount of heat generated that it can even melt that particular material. So in this case, we can melt that particular conducting material there which we have kept, and this we use it as an induction furnace there. Third application is there in speedometer. In the vehicle, you must have seen there is a speedometer which gives the speed of the vehicle with which it is moving. There also you have a magnet attached with a wire which basically passes there and gets attached to the axle of the wheel. So in that case, it is as it is connected to the wheels there, so if the wheel is rotating, its axle is rotating, and along with the axle's movement, this wire is also turning. It is moving there. And at the end of that, there is a magnet attached. So that magnet will also rotate. Now this one is kept inside a hollow aluminum cylinder. So as the magnet inside it is moving or rotating there, so magnetic flux linked with that hollow cylinder will also change. So it will develop an eddy current in that conductor, that is the hollow cylinder there. So in that case, this cylinder will just oppose in a direction to oppose the cause of it. That is, the cause is there, change of the magnetic flux there. So that one will try to turn so that it can oppose. Now, by how much amount it will turn, it will depend at what rate this wheel is rotating or the magnet is rotating. And that one will depend upon that with what angle that one gets turned, that is the cylinder gets turned. And along with that cylinder, we attach a pointer there. So this pointer will indicate the speed with which that vehicle is moving there, because this is basically connected to the wheels there. So if the wheel is rotating at faster rate or particular speed there, in that case the magnet is also rotating with that particular speed. So in that case there will be eddy current developed, which is proportional to the rate at which this is rotating. And this eddy current which is developed there will just make the rotation of this hollow cylinder there to a particular point where it will acquire equilibrium. And the calibration is done so that we can measure what is the speed of that vehicle at that particular moment. So this is how the speedometer works. Similar effect will be there in the magnetic brakes also. In magnetic brakes, if suppose a vehicle is going basically in the magnetic trains, another we find that one, or in the train, if you consider, we have the magnetic brakes there. So there, if suppose the wheel is rotating there is a plate there attached with that one without making physical contact there. So when we want to stop that, we pass electric current. So there is the eddy current developed. And as the eddy current will be developed, it will try to oppose the motion. So motion of the wheel will be opposed. And as a result, since the strength of the current will be so large that it will try to oppose the motion very fast. And in that case, this rotation of the wheel will be opposed. So it will brought to rest very soon. The advantage of the magnetic brakes are there as they are not making any physical contact there. In that case, wear and tear is not there. Secondly, that change will be very smooth. That means it will be a smooth stopping of the vehicle. Otherwise, normally when you apply the brakes there is the jerk there. Jerk motion is there. There it will not be such type of jerk there, and it will stop very smoothly. So these are some of the advantages or applications of